Alright, so I just wanted to review a few basics related to your lab. In physics, we have this thing called an Atwood's machine. Okay? And it looks like this. Has two masses. So this friction is considered to be, this pulley is considered to be frictionless, oftentimes. That means that, the tension everywhere along this rope, the tension is the same. Well, it's the same magnitude, so I should correct that. The same magnitude. So, what the pulley does, pulleys in physics change the direction of a force, but not the magnitude. Okay? So, now what we have in this lab, you can see why it would be called a modified Atwood's machine. So that's the name we physicists give to this apparatus, Atwood's machine. Okay, I'll call this object 1, this object 2. For you, this is a cart. This is a pulley. For us, it's a low friction pulley, and this is a hanging mass. Okay, so just to review basic concepts, if we do a force diagram for the cart, we'll get weight going down. I'll call this W1. Right, we'll got normal going up, and then we have tension to the right. And our vector sum diagram, you'll see, looks very similar. You got normal up, you got tension to the right, you got weight down, weight 1, tension, normal. And in a different color, I'll draw the total force acting on the cart. So that's total force acting on cart. Okay? Then, over here, I'll draw a force diagram for the hanging mass. So I got W2, call that vector. I got tension up, right? If I add those vectors, I got W2 down, tension going up, and my total force will be going down, right? And this is the total force acting on hanging mass. Okay? Now, some basic ideas that are important here is the magnitude of tension force is the same everywhere along the rope. So this tension and this tension should be same magnitude. Another important concept that we aren't capturing here is that the net force on the cart is probably much greater than the net force acting on the hanging mass. So the sum of the forces acting on cart should be a lot greater than the total force acting on hanging mass, since the mass M2 should be far less than M1. So what I'm trying to say is that and also since same acceleration, that's really why. Because for two objects with different mass to have the same acceleration, these two objects have different mass, but they have the same acceleration. So the one with less mass, probably the hanging mass, is going to require less total force to yield the same acceleration as the cart. They have to have the same acceleration because they're attached by a string, but the total force acting on the hanging mass is much less than the total force acting on the cart. But I found that this particular problem especially is really useful to really look at as one system of two objects. Let me do that. Let's see what happens. Okay. So here's the same modified Atwood's machine. This was mass 2. This was mass 1. All right. Now, consider the two mass system, right? Well, it's a little weird to think of it this way, but for the force of tension, if both objects are considered to be one system, right? Both objects are considered one system. What happens to tension? Well, tension, force, does not exist since, well, M1, rope, M2, let's make all of those part of our system. Okay? That'll make things a lot simpler, right? And the weight of object 1 and the normal force add to 0. So this allows us to identify, this really allows us to identify the total force acting. Identify the total force that causes the entire system to accelerate. That's what's cool about this strategy, okay? So the only force acting on this system that doesn't add to another vector to be 0 is going to be W2. So W2 is the total force acting, okay? Because that's the only force that doesn't add with another force external to our system to be 0. So all the other forces acting on our system add with another force, okay? Tension doesn't exist because tension is inside our system. But W1 is external to the system. The Earth pulls on that part of the system. But that force adds with normal to equal 0. But the weight of object 2, which is external to our system, so what did I just do here? So that is external. So W2 is the only net force acting that is external to our system. Okay? So what does this all mean, right? Well, when you graph your data, right? Acceleration versus mass. First off, which mass are we talking about? Well, you need to add M1 plus M2 in kilograms because both objects are really part of our system. You should also keep track of hanging mass so that later we can identify the total force acting during this investigation. I'll call it investigation 1. Okay? And when you do part 2, which is acceleration versus total force, now you know that it's really just the weight of object 2 that's responsible. And when you do this investigation, part 2, in part 1, hanging mass was constant, right? That was important. When you do the second investigation, make sure that the mass stays constant. Well, which mass? This is an important question because we're not talking about just the mass of the cart now. 2 objects. Hanging mass plus mass of cart equals total mass. Just like this. So we're going to have to keep the total mass constant. Now, that does create a logistical problem. Tomorrow in class, I'm going to ask you, how do you keep the total mass constant while changing the net force? How are you going to make net force your independent variable and change it while you keep the total mass constant? There's actually a cool way of doing this. You have to think about it, though. So, again, I'm challenging you to think about how can you keep the total mass changing while the total... Sorry, I said that wrong. How can you change the total force while keeping the total mass of your system constant? One last time. How are you going to change the total force acting on your system? How do you change the total force acting while you keep the mass, the total mass, constant? How are you going to do that? Anyway, hopefully you figure that out before tomorrow. If not, don't freak. We'll help you out. But surely talk to a friend about it. Anyway, I hope this helps. Helps you understand basic concepts. And have a good day. Thanks for watching.